Hello, everyone. Welcome all back. For the next session, we'll have Carlos Alagin talking a little bit about learning. AI and deep learning in general has been a hot topic for the past, I'd say, 3 to 4 years. So please take it away.
Hello, good morning, everyone. I'm here to give you a basic introduction to deep learning, seeing that is a hot topic nowadays. Let's I'll talk a little bit about myself. I'm a developer in Cittatech for 2 years now. Since I joined the company, everyone just talked about AI and what we should do with machine learning. We are a company that works with ITS, so it's very important for everyone to know and be on the same page about that, or what applications we can make. So I'm here to present you a little bit about this specific topic. So without further ado, let's start. Here's my agenda. We'll talk about what is deep learning, why do we need deep learning in applications. We will make a comparison with machine learning and deep learning to know the differences and when it's better to use the classic machine learning and when is the best time to use deep learning. We'll talk about the applications that nowadays the big players are developing and trying to bring to us. After that, we'll go deeper inside the deep learning topic and talk about artificial neural networks. They are the secret sauce of deep learning. We'll talk about activation functions just to know the concepts and how it works, and we'll talk about the how an artificial neural network works. So, and after that, I'll talk a little bit about some deep learning algorithms and what are their purpose for using. So, what's deep learning? Deep learning is a subfield of machine learning, which deals with algorithms inspired by the structure and the function of the human brain. So we have artificial intelligence as our main topic here, that talk about the concepts, the philosophy involving the capacity of the machine to learn and to do stuff by itself, evolve the algorithm all by itself. And inside that, we have the machine learning that is exactly the application of the concepts and the philosophy of artificial intelligence to solve problems. And deep learning is the application of machine learning that uses complex algorithms and they use the deep neural networks to train a model to solve some kind of problems. So why do we need deep learning? When you have a huge amount of data with structured and unstructured stuff like images or audios, it's hard to people to, for example, I want to extract the characteristics of a cat and say that a cat is a cat given an image. So as I'm an IT specialist, but I'm not a biologist. I don't know what to say of what are the main characteristics, the specific characteristics that defines a cat. So to perform an algorithm that extracts this stuff in a complex way, it's good to use deep learning. And nowadays we have like huge amount of data. So the bigger the data is, the more complex, the longer it will take to process this data. So deep learning is really good to use because the bigger the data, the best performance it has. And it also helps the analyst with the feature extraction. But what a feature extraction is? Let's use this example of a human face. Feature extraction is just the algorithm will take your face and define certain points that are important to you to define that this person will be recognizable by the algorithm. So the distance between the eyes, or the distance between the brows, or the relation between the distance of the nose to the mouth and the mouth to the chin. All of this are things that can be extracted, and the algorithm will process it and will recognize your face. What are the main differences between machine learning and deep learning? Machine learning, the classic one, the algorithms are directed by the analysts. So the analysts have to know how to guide the algorithm to perform to extract the features, to know what kind of problem it will solve, to orchestrate the whole process. And in deep learning algorithms, you just give in an input and you have this information all labeled, and the algorithm will be responsible to do all the stuff. It will extract the features automatically. It will do the classification automatically. To show an example, the process will be something like this. You have an input that is a car, and you will have here an analyst dictating what are the features that is going to be extracted in this car, and we will have an artificial neural network saying doing this classification, and then we have the output if it's a car or not a car. In deep learning, we have kinds of nets that do the image extraction and do all the classification and do the feature extraction by itself. So the analyst doesn't need to worry about that. And coming back, the output, as I said before, the bigger the data, the best performance the deep learning will have. So here is a small chart of how it works in terms of data per performance. If we have a data set that is considered small, the traditional machine learning will process it faster, and it will give you better results. But as the data starts growing up, we'll see that the deep learning networks will have better performances. And another step that we can differentiate the machine learning from the deep learning is the machine learning. The output is usually a numerical value or score or a classification. Now, on deep learning, the output can be like a score, an element, a sound, or a text, or some whatever. So I'll talk about the applications that nowadays we have in the deep learning area. We have like autonomous vehicles, we have personalization and recommendation systems, we have virtual assistants and facial recognition. We also have robot advisors. We have investment platforms that are all digitalized, sentiment analysis, text generation, natural language processing, and in healthcare, a lot of stuff. But talking about autonomous cars, we all know that Tesla is a big player, but what caught my attention is Uber AI Labs in Pittsburgh are engaging some work to make autonomous cars a reality, because it's their business. They want it on the streets. So deep learning is guiding this initiative for the automotive part of this business, and they are trying to enable driverless cars to navigate by exposing it to 1 million of scenarios and to make it safe and comfortable for the clients. And they are using data from sensors, from GPS, from geomapping, all combined together in deep learning to create models that specialize and identifying paths, street signs, or dynamic elements like traffic or congestion and pedestrians. In the area of personalization, it's already a reality. We have like big players in e-commerce and entertainment like Amazon and Netflix, and they are building their deep learning capacities to provide you with a personalized shopping or entertainment system. They use it by creating to the client a pattern that are based all on deep learning. They try to push out options in your subconscious based on preferences, recently visited items, affinity to brands or actors, and overall browsing history on their platforms. On the smartphones area, what I found most interesting was the virtual assistants that like Amazon Echo or Google Assistant, the Alexa and Siri from Apple. They are all exploiting deep learning capabilities to build the customized and user experience for you. They learn to recognize your voice and accent and present you with a human experience through a machine by using deep neural networks, imitating not just the speech, but also the tone of a human. The virtual assistants help you shop, you navigate through the internet, you take notes, translate them to text, or even make an appointment for you. And another algorithm really present on smartphones is the facial recognition. For example, the iPhone's facial recognition uses deep learning to identify the data points from your face to unlock a phone or spot you in images. The deep learning helps then to protect the phone from unwanted unlocks and make your experience like hassle-free, even when you have changed your hairstyle or you lost weight or you're in poor lighting. Sorry. Every time you unlock your phone, deep learning uses thousands of data points to create a depth map of your face, and the inbuilt algorithm uses those to identify if it's really you or not. Another very interesting is the text generation. So some algorithms, on deep learning, they will create original text, even poetry, as they're evolving very fast. Like everything from the large data set, text, internet from Shakespeare is being fed to deep learning models to learn and emulate human creativity with perfect spelling, punctuation, grammar, style, and tone. So it likes the algorithms are learning how to imitate humans, even in creative ways. And natural language processing is another very, very used nowadays. People are doing a lot of research on that, and it's taking this amount of research, taking the natural language processing to from good nowadays to great in terms of use, maturity, and sophistication. The organizations are using that to enhance their complexities. And using on the areas of document summarization, question answering, language modeling, text classification, sentiment analysis, or some and some other stuff of applications. Like people say that several jobs worldwide that depends on human intervention for verbal and written language expertise will become redundant as the NLP matures. In healthcare, there is another sector that we've seen a tremendous growth. We've seen like early detection of diseases and conditions, quantitative imaging, robotic surgeries, examining genetics to prevent future risk of disease and negative health episodes, and decision support for doctors and people that works on the healthcare area. I think they are the same points that are turning into important in healthcare. So as we are a company that works in transportation area, I'm going to talk about a little bit on the applications in transportation. I can say deep learning nowadays can make like traffic characteristics prediction. That is one of the most considered applications, because traffic characteristics information can help drivers to choose their roads more wisely and traffic management agencies to manage traffic more efficiently. The main characteristics of interest are traffic flow, traffic speed, and travel time. Since these characteristics are not mutually exclusive, methods that are used to predict one of them can also be used to predict the value of the remaining features. We also have like traffic incident inference that the goals of it is to map the risk for a given location as well, given the traffic features and the time that is happening the analysis. So although there are parameters such as drivers' behavior that are not very predictable, there are several key features that can help predict the traffic incidents. We have one that is very common nowadays. I can say that is common, like is vehicle identification. The applications varying from calculating time to time along the road, and you see that how this vehicle is behaving, and then you detect it by his reading the vehicle plate. So another application that we see is traffic signal timing, that for many years there were researches on optimizing signal light timing to have the best performance, and it has been one of the greatest challenges in the transportation field. The results of studies in these areas have endowed traffic agencies with analytical models that use mathematical methods to address this optimization problem. However, modeling the dynamics of traffic to achieve the best performance has taken a new path. This is because the nature of reinforcement learning has facilitated its application in different studies to find the best traffic signal timing. An interesting application is the ride sharing. Nowadays, to increase the city planning performance and also passenger satisfaction, the companies are with the increasingly optimal routing maps. They are using these maps to take into account data such passenger demand and particular places and times. So they adopt deep learning to make predictions even more accurate compared to the existing machine learning techniques. And the vision recognition tasks are the applications that provides a suitable roadway infrastructure for driving vehicles, to endow the autonomous vehicles with safe and reliable driving strategy. Basically, it's to detect holes and inconsistencies on the road and stuff like that. So let's talk about the main component of deep learning, that are the artificial neural networks. let's talk about the main component of it, that are the neurons. And neurons are the basic functional units of the nervous system, and they generate electrical signals called action potentials, which allows them to quickly transmit information over long distances. Almost all neurons have three basic functions for the normal functioning and of all the cells in the body. And these are: one, to receive signals or informations from outside. The second one is to process the incoming signals and determine whether or not the information should be passed along. And third is to communicate signals to target cells, which might be other neurons or muscles or glands or whatever. Now let's understand the basic parts of a biological neuron. We have the dendrite that are responsible for get incoming signals from outside. Sorry. We have a soma that is called also as cell body, that is responsible for processing the input and deciding whether a neuron should fire an output signal or not. We have the axon that is responsible for getting the process signals from soma to the relevant cells, and we have the synapses. The synapses are the connections between an axon and other neuron dendrites. And we have an artificial neuron. An artificial neuron is also known as perceptron, as the name given to it. It's the basic unit of a neural network. In simple terms, it's a mathematical function based on a model of biological neurons. It also can be a simple logic gate with binary outputs. They have three main functions also. They take the inputs from the input layer, they weighs they separately and sums them up, and they pass the sum through a non-linear function to produce an output. And these neurons consist of four parts: the input value or input layer, whatever you choose. We pass input values to a neuron using this layer. It might be something as simple as a correction of array values, and it's similar to a dendrite in the biological neurons. We have the weights and the bias. Weights are a collection of array values which are multiplied to the respective input values. So we're going to multiply the x1 with the weight 1, and so on. And next we add the bias value to the weight sum to get the final value or prediction by our neuron. We have an activation function which decides whether or not a neuron's fired, and it happens inside the neuron. And we have an output layer. And the output layer gives the final output of a neuron, which can be passed to other neurons in the network or taken as the final output value. But what happens inside the neuron? We take a sum of the multiplied values from the input and the weight, and we call that a transfer function. So it will sum all the inputs multiplied by their weight, doing a weighted sum, and they will transmit it to an activation function, and this activation function will be responsible to say if the signal will be propagated to the output or not. So if we compare a biological neuron to an artificial neuron, we'll have the dendrites as the inputs, the cell body as the nodes, the synapses as the weights, and the axon as the output. So I'm going to talk a little bit about the activation functions, just to for you to know the concept of that. But basically, we have these are three of the most famous activation functions. What it does is just it will receive a signal, and depending on the signal value, it will return a value to the output. For example, here we have the sigmoid that if we receive a negative value, it will be less than 0.5, and the minimum value is close, really close to 0. And if it's a positive value, it will get closer and closer to 1. So the most famous used nowadays is the ReLU. The ReLU, if the value of the signal is negative, it will return 0. And if it's a positive value, it returns the value itself. So given these concepts, let's use two here. Oh, I hope so. it will get better, I guess. So let's see how an artificial neural networks work. For this, I will give an practical example of how a single layer neuron works. We have here an example that we have the inputs that is 0.8 and 1.2, and the weights here are defined. By the way, the weights here are defined by the algorithm randomly at first, and after that it will get updated as long as the time goes. We have a bias. A bias, it's a hyperparameter that is defined by the analyst. There is another one that I'm going to talk about it later. And after that, they will perform the transfer function, and will pass through the activation function, and will give it an output. In a simple way, talking about math, it will get the weighted sum with summed by the bias, and it will make the calculation, and it take this value that is 2.2. As we used here the ReLU function, so if it's 2.2, the combination is between 0 and max. It will return for us a signal with 2.2 that will be passed along the other layers of our neural network. And now that we have a basic understanding of how biological and artificial neurons are functioning, let's take a look at the architecture of an artificial neural network. They generally consist of a collection of connected neurons, and these artificial neurons try to model the biological neurons of our brain. The connections between the neurons are called weights, and when an artificial network learns, the weights between the neurons are changing. So does the strength of each connection between the nodes. Here we call the first layer the input layer. It is responsible to receive the input X of data from which the neural network will learn. Using an example here, a quick example of, for example, like classification of handwritten numbers. This input layer would represent the pixels, each pixel of the image X, transformed in a vector of RGB numbers. For example, the first pixel of image is returning a black pixel, so it will be the first node here, an object with RGB 000, and the last one is returning me a white pixel, so it will return here an object with 255, 255, 255, and so on. So the last layer is called the output layer, and is representing the result that the neural network came up with. So it will be a lot of calculation. It will do a lot of calculation here between the layers that I'm going to explain later. And here would be like a classification. In this example, let's imagine that we are trying to classificate 4 kinds of objects. And here in the output, we have each one as a classification of each one. So if this neuron is activated on the output, I would classify it as a cell phone, and here a car, and here a plane, and here a bike, for example. The middle layers that are called hidden layers, they are responsible to extract the features, and along the way, they will do different. They will extract different things. Here, for example, I can be extracting the rounds or the sharp corners that are relevant in the image. And here I'm doing, I'm detecting the borders, what is happening in the borders. Or here I'm detecting like a shape of basic shape of an object. And the combination of these characteristics is going to give me an output. So to go deeper about, we will consider a smaller example, just to know how the training works itself. As I mentioned earlier, each connection between 2 neurons is represented by a numerical value that we call weight. As you can see here in the picture, each connection between the two neurons are represented by a different weight. So we have the indexes here, and the combination of that will generate a weight matrix. This weight matrix will be responsible to calculate, will be used to calculate the transfer function, and after that, the activation function of each node. Here, as you can see, we have here a vector, and here we are doing the calculation that will generate this output H1, H2, and H3. And this method is called forward propagation. With the input of vector X and the weight matrix W connecting the 2 neuron layers, we compute the product between the vector X and the matrix, and the result again is a vector which we call a Z, that can be represented here by this example. We have a vector X1, X2 that represents the inputs, and we have the weight matrix. To get clear, the Z1, for example, is the sum of X1 multiplied by H11 with X2 multiplied by W21. So these are the transfer functions that's called Z, and after that we will apply a sigma function, that is the activation function, will be the ReLU or the sigmoid or the hyperbolic tangent. Oops, oh sorry. And after we apply that, we will have an output that is the vector H1, H2, and H3 in that case. After we do all that forward propagation here, this one will be the input for this layer, that will be the input for this second layer, and so on. After that, we will apply all the functions here, the activation functions, and then in the end we will have a final output. So in the end, like we all have labeled information there. So if a person, we were predicting a handwritten number, and we wrote the number 1 and showed that to the neural network to classify it. It will do all the process of forward propagation. It will give us an output. But I know that it's a number one. It was labeled before that it was a 1. So in the end, we have a formula called loss function that is the difference between what the network gives us and what we were expecting to be as an answer. And then we do all this calculation to see like how far we are from the correct answer. And what we got to do here to a neural network be considered good or to be more accurate, we need to minimize the loss function. So the difference between the prediction and the label must decrease. And since the loss function depends on the weights, we must find a set of weights for which the value of the loss function is as small as possible. And the method of minimizing the loss function is achieved mathematically by a method called gradient descent. I'll talk about now the gradient descent and how it works. During gradient descent, we use the gradient of a loss function to improve the weights of a neural network. So to understand the basic concept of the gradient descent process, let us consider a very basic example here of a neural network consisting of only one input and one output neuron connected by a weight W. So here are some values that were preset by me. Here we have the weight as 5, the input will be 2, and we have the exit or the output that is 10, and the weight, the expected output by the analyst was 6, for example. So for this function to be like correct, my weight should be 3, because if you multiply 2 by 3 here, it would be 6, and the network would be like correct. But as you can see, there's a certain difference between the weight that the network gives us and the value that were expected by us. So what we have to do is to define this in the loss function and decrease this difference. So we use the loss function now to calculate the difference between the expected exit and the given exit, the given output. And the goal now is to repeatedly update the weight parameter until we reach that optimal value for that particular weight. And this is the time when we need to use the gradient of the loss function. So using in this next step, we calculate the derivative of the loss function with respect to this parameter, and will give us a result of 8. So in the end, when we get this result of 8, which give us the value of the slope or the tangent of the loss function for the corresponding point on the x-axis at which our initial weight lies. So this tangent points towards the highest rate of increase of the loss function and the corresponding weight parameters on the x-axis right here. This means that we have just used the gradient of the loss function to find out which weight parameters would result in an even higher loss value. But what we want to know is exactly the opposite. So we we can get what we want if we multiply the gradient by -1, and this way obtain the opposite direction of the gradient. And this way we get the direction of the highest rate of decrease of the loss function and corresponding parameters on the x-axis that cause this decrease. Here we have an example of how we will calculate the new weight given the loss function. So we had all this calculus before to discover that the loss function here had a value of 8. And then to calculate the new weight, we use the old weight minus epsilon, that I'll explain in a moment what it is, and the derivative of the gradient descent. Epsilon is another hyperparameter that is called learning rate. Like the bias that we talked about previously, these parameters are determined by the specialist, and the learning rate determines how quickly or how slowly you want to update the weights. But keep in mind that the learning rate is the factor with which we have to multiply the negative gradient, and that the learning rate is usually quite small, because if we have a learning rate too big, it will learn too fast and starting to memorize stuff instead of learning. In our case, I selected the learning rate is 0.1. So as you can see now, our weight W after the gradient descent is now 4.2 after this calculation of the new weight. And we will do this step for all the weights given the loss function. We will update all the weights in our neural network. So when you get the loss function here, you will update this weight matrix, and after that, this weight matrix. And this method of applying the gradient descent step is called backpropagation. So a network, each iteration that it has, we call epoch. And each epoch, we will have a forward propagation that the signal will be propagated through the net, and it will give us an output. We will calculate the loss function, and we'll do the back propagation process that we will recalculate all the weights on the net and goes to another epoch, and then repeat the process until we have an accurate neural network. So this is how an artificial networks work, and I'll talk a little bit about the deep learning algorithms. These are the most known algorithms nowadays. We have the KNN, that is the K nearest neighbors, that is very simple and a supervised algorithm to solve both classification and regression problems. We have the K-means clustering, that it assigns points to categories or clusters. Is very good for clustering and classification. And they find the mean between data points. We have the hierarchical clustering that groups similar objects into clusters. We have the artificial neural networks that we talked about here, how it works. Being more specific, we have the recurrent neural networks that are artificial neural networks that uses the output from the previous step as the input to the next step. So in a lot of situations, it has a better performance than a classic artificial network. And we also have the convolutional neural network. The convolutional neural network is the best one to classify images, because it uses a lot of filters and extract features on images using each layer, they have tools to extract image features better. We have linear regression, that is a classic one, that is a statistical method to generate like insights. And we have the logical regression that uses when the data is linearly separable. One of the main good stuff about the artificial networks, or any of these networks here, is that they solve problems that are non-linearly separable. So complex problems, that's why we use neural networks. So if you have any questions, please feel free to.
Hi, Carlos. Yes, that was very interesting. George has a question here. Hello, as we know, neural networks with machine learning is specialized on some specific category or tasks. Is it the same for deep learning, like only for images or only for sounds and so on? Thank you.
Hello, George. What I can say is that we have better solutions for each specific stuff, but we can use, for example, recurrent neural networks to classify images, as well as convolutional neural networks. This doesn't make a difference, but depends on your experience created as an analyst, and what technique you think if it's better to solve the problem. I can't tell you that one is better than another, because this experience you only get it with time, and then you get the knowledge on how to solve some kind of problem using. It's all experimental. You have to experiment the techniques, and then you get the results and you compare the results, and then you create a base knowledge. And when you have a new one, you can use transfer learning from the experiences you had in the past and apply that on the new problem you have to solve.
Okay, makes sense. Julian asks, in your opinion, how important is it to understand the math behind machine learning and deep learning? For instance, forward propagation, backward propagation, etc., versus just using libraries that get it done behind the scenes, like TensorFlow?
Okay, the importance, I think, on knowing the math behind it is for you to understand what to expect from that. If you know that a neural network, what power do you have on your hands? If you know the math behind that, you would know, like, you can get the specific stuff from each one and have a base to apply better on a solving problem. I usually say that the math behind that is not that hard. It's complex, but if you start to work with that and make some studies, you see that it's not that hard. And at the same time, you will learn that given unstructured data, for example, I can do a process, a complex process, and transform everything in numbers. And this power will help you to understand things differently. You can stop thinking about an image as an image, and you can start thinking of an image in a math way that is an object of a lot of numbers there. So understanding the math, I think that is basic for anyone who wants to enter this area of deep learning.
So let me ask you on a different way then. If a team were to embark on starting an AI or deep learning, machine learning initiative, do you think that the first step should be to try to use a library like TensorFlow or one of the services provided by, say, Amazon or Microsoft, or they should look into one of those machine learning courses that teach you the basics first and then embark on to try to implement something?
Well, from my point of view, I always like to study the concepts before using any tool. When you're implementing that, if you don't know the basics of what is backpropagation, what are the hyperparameters, for what the hyperparameters are used, how the learning rate works, mathematically talking, how you can be more accurate to achieve better results on your net. If you don't have these concepts really well designed in your head, you won't have like a good initial experience using the tool.
Okay, and AI also has been touted as an answer for everything, like it can do everything. But in your opinion, what are some areas that it shouldn't be used for?
It shouldn't be used, AI? I guess that all depends on what people want to achieve. If you're using the technology, whatever it is, to do good for human beings, or
actually no, it's a slightly different question. So what areas that I guess I'm not talking about exactly the use case, but for instance, it's really good for recommendation, but it's not good for.
Okay, I got you. For example, to solve statistical problems, I don't see any fit on using AI for that, because we have very relevant, and if I have linear problems on, for example, calculating how much a building worth nowadays, we can use only linear regression to do this stuff. So I think you have to look at the problem and see if the problem is complex or not. Depending on the complexity of the problem, you apply AI, because it's like you give a gunshot on an ant. It doesn't make sense to you to use AI on very simple problems.
Okay, I think we're done with questions. If you have any additional comments.
Just like I would like to thank the opportunity to talk. It's my first time talking in English, so it was a good experience. Thank you. I want to thank everyone for their time to present a thing that is a field that I've been studying, and we're trying to apply in Cittatech here. So, and I would like to thank you, Takeshi, for the opportunity. And that's it. Everyone have a good day.
Thank you.